Dear students, today's video deals with repeated projects and replacement decisions, which have to be treated a bit differently than one-off decisions. I will now show you how. Here we see two different investment projects, A and B, which have different lifetimes. A starts with an investment in T0 and runs for 3 periods and gives us a payoff of 43 in each of these periods, while project B runs for a total of 4 periods, giving us a payoff of 34 over these 4 periods. Of course, we can calculate the NPV for this project at an opportunity cost of capital of 10%. You can pause this video at this point if you want to make the calculation yourself. Are you ready? So here's the result. Project A has a NPV of 6.93, while investment B has an NPV of 7.78. Which one should we choose? So from the NPV perspective, investment B seems superior. However, it will also depend on the nature of the project. So far, we mainly looked at one-time projects, which means that a project can be only undertaken once. A prototypical example would be different ways to exploit a coal field. After you've done the project, the coal is gone, and therefore you do not need to think about whether the project can be repeated in the future. In this case, you can simply look at the NPVs as they are. And in this case, B is better. However, there often are projects that can be repeated in the future. In this case, for simplicity, we will think about infinite identical replacement, which means that once a project comes to the end of its lifetime, it is replaced by an identical project, which means that the project more or less starts all over again. A simplified example would be cars in a car rental firm. Once a car has reached the end of its lifetime, the firm buys an identical car and starts the process all over. Of course, we here neglect technological progress that would change the nature of the projects. And here, simply comparing the NPVs would not take into account that we have different points in time where the investments are replaced. Investment A has a shorter lifetime and is already replaced after 3 periods, while investment B is only replaced after 4 periods. To make a decision here, we need to convert these cash flows we get from the projects with different lifetimes into equivalent annual cash flows over the lifetime of the projects. So what do we mean by equivalent annual cash flows? For this, it is helpful to think about a project on a timeline. Here, the graph shows the timeline of a repeated version of project A. Here we see the initial investment in T0, which was minus 100, and the cash flows in the following 3 periods. We now assume that in period 3, project A is replaced, which means we again invest 100 and then obtain a cash flow of 43 in the following 3 periods. In period 6, we do it all over again, and so forth until infinity. We can then represent this project by the NPVs, because in each of the future periods we get an NPV of 6.93 as we did in t equals 0. So we now have represented the project by the NPV it generates every 3 years. And equivalently, this can be done for project B. How does this help us now to compare the different projects? Well, with project A, we now get the NPV every 3 years, while with project B, we get a higher NPV, but only every 4 years. To compare these payment streams, we need to convert them into annual cash flows. And we have a method to do that. As you might remember, the annuity factor gives us a corresponding relationship between an NPV and an annual payment. So what we actually need to do is to use the annuity factor for the lifetime of the project and the respective opportunity cost of capital. So we take the NPV of project A and divide it by the annuity factor for opportunity cost of capital of 10% and 3 years, because this NPV occurs every 3 years. Then we get an annual payment of 2.79. Similarly, we do that for project B. Here, of course, we have to use the annuity factor for 10% opportunity cost of capital and 4 years, which gives us an annual payment of 2.45. And we see that with replacement, project A is better because it provides a higher annual cash flow. In a similar way, we can handle replacement decisions, which are simply about how long to use an asset. For example, how long to use a machine. We can decide that if we treat this replacement decision as choices between two projects with different lifetimes, where the shorter lifetime represents an earlier replacement of the machine, while a longer lifetime represents a later replacement of the machine. So for replacement decision, the procedure would be like this. First, we would determine all reasonable replacement dates. So when would it make sense in our production cycle to replace a machine? Then we estimate the cash flows and the salvage values. Salvage value is the selling price of the machine or asset we use at the point of termination. And it is, of course, important to take it into account because usually if we replace an asset earlier, it has a higher market value and can be sold at a higher price. We now treat these alternatives as separate and mutually exclusive projects. Mutually exclusive because we can only make this replacement once. So while we without replacement just compared the NPVs, with infinite and identical replacement, we compare the equivalent annual cash flows.